Okay, we are about to begin the afternoon session. First speaker, Ashoke Sen from Allahabad on Tachyon dynamics in open string theory.
Thank you. Okay, so it's a pleasure to be here. And the title of my talk, as you heard, is Tachyon dynamics in open string theory. And in this talk, the goal will be to construct time-dependent solutions in open string theory that describes rolling of a generic tachyon away from the maximum. And the talk will be divided into two main parts. First, I'll discuss the method of construction of these solutions. It will be an iterative method. And then I'll discuss specific examples where one can get explicit analytic results for the tachyon dynamics. And here are various references which are relevant to this talk. So let's begin with considering an unstable de Bruijn system with some tachyon field phi, and at this stage I will not commit myself to what tachyon we are talking about. It could be a tachyon on an say unstable de Bruijn in type 2 string theory or bosonic string theory, or it could be a more general tachyon like, for example, on a D0 D2 system in superstring theory. Now, given this tachyon, we know that the potential of the tachyon has a maximum at phi equal to 0, so the potential has an upside down shape like this. And if phi had been an ordinary scalar field with standard 2 derivative action, then we know that there exists a 2 parameter family of classical solutions which will describe rolling of the tachyon away from the maximum. And these 2 parameters are labeled by the initial conditions on phi as well as on the time derivative of phi. However, if the theory has time translation invariance, and those are the kind of theories we are considering here, then we can use time translation invariance to set either the initial value of phi or the initial velocity to be 0 at the origin of time. That is the way we will choose the x naught equal to 0 point, and this will give rise to 1 parameter family of inequivalent solutions of the equations of motion, and this parameter can be taken to be, for example, the energy of the trajectory. Now, the question that we will ask is it possible to find a similar 1 parameter family of time dependent solutions which describe the rolling of an open string tachyon? And our analysis will be at the level of classical open string theory, which means that we will consider the limit where the string coupling is going to 0, but we will try to keep all orders in alpha prime. And the general strategy that we will be using for considering time dependent solution is to begin with not a time dependent solution but a time independent solution which depends on some spatial coordinate x. It could depend on more than one spatial coordinate, but one of them will be spatial in the sense that this is what we will eventually interpret as a Euclidean time. So, given such a solution, we can simply replace x by minus I times x0, where x0 is the time coordinate, and this will generate a solution of the equations of motion, a time dependent solution of the equations of motion if the original solution dependent on x. However, we have to make sure that the solution that we get this way is a real solution, because after all we have some reality condition on various fields and we do not want some fields to become imaginary under such replacement. Now, to see more explicitly how we proceed, let us suppose that the tachyon has a mass square equal to minus m square, it is negative, and so in this case the linearized equations of motion for the tachyon field around the origin will be of this form, and we can solve this. It has 2 independent constants of integration, but as I said, we can consider using time translation invariance 2 inequivalent initial conditions. In one case we set the tachyon initially to be some constant lambda and the velocity to be 0. This has a solution of the linearized equation of motion of this sort, and we can also consider the other boundary condition where you set the tachyon to 0 but the velocity to be non-zero, and this has a solution of this form. This will correspond to a configuration where the total energy is less than the value of the potential at the origin, and for this the total energy will be larger than the value of the potential at the origin. We will concentrate for most part on solutions of this type. However, I should just say that whatever I say for solutions of this type can also be generalized for solutions of this type. but just for definiteness we will concentrate on the first type of solution. So if in this solution we make a replacement of x naught by I times x, where x is a spatial coordinate, then this gives a solution of the linearized equation of motion as a function of one spatial variable, which is of this form. This is simply a replacement of x naught by I times x. So our goal then, okay, I'll put it up. So our goal will be then to construct a one parameter family of solutions which is labeled by this parameter lambda, and this should reduce to this form when we take lambda to be infinitesimal, because this is the solution of the linearized equation of motion. And this will be done by using the well known correspondence between solutions of string equations of motion and conformal field theories. So what we need to construct is a one parameter family of boundary conformal field theories which is labeled by this parameter lambda. Now let us denote by V phi the vortex operator for the zero momentum tachyon, whichever tachyon we are considering in this case. So if we switch on a tachyon equal to lambda times cos mx, this will correspond to adding a perturbation to the original conformal field theory of this form. So this cos of mxt comes from this cos mx here, and this V phi of t comes because the tachyon, the zero momentum tachyon, is described by this vortex operator V phi. And lambda is the parameter, and it's a boundary perturbation because after all we are considering open strings. And by construction this has dimension 1. This operator has dimension 1 because this is a solution of the linearized equations of motion. Now we can consider two cases. One is a spatial case, and this will correspond to the case when this operator, the combined operator that we have here, is an exactly marginal operator. If this is an exactly marginal operator, then this perturbation will describe a boundary conformal field theory for every finite lambda. That is what we mean by saying that this is an exactly marginal deformation, and this then in turn generates the one parameter family of Euclidean boundary conformal field theory that we have been looking for. And given this one parameter family of boundary conformal field theories, we can then make a replacement of x by minus I x0 and get the rolling tachyon solution of the full string equations of motion. However, the more generic case is the one where this operator is not exactly marginal. Of course, it still has dimension 1 by construction. In this case, just perturbing by cos mx times V phi is not going to generate a conformal field theory. So we have to change our tactics, and the reason that it doesn't generate a conformal field theory is because the beta function receives higher order corrections. So in this case, the way one can proceed is to consider a different perturbation, not this one, but simply change m to some parameter omega. So this is now no longer dimension 1, it has a dimension which is given by omega square minus m square. So if we now compute the beta function associated with this coupling lambda, then it has a contribution from the dimension, and then of course it has higher order contribution which can be thought of as a power series expansion in lambda. And now the idea is that for every given lambda, at least for small enough lambda, we can try to find omega such that beta lambda is 0. So the leading order, this term can be ignored and we get omega equal to m, which gives you back this perturbation. But in general, omega will be given by m plus a term of order lambda square, and so by adjusting omega for every lambda, we construct a one parameter family of boundary conformal field theories, which is what we want. And then we can again make this replacement to get the corresponding rolling tachyon solution. Now I should note that for this procedure to work, the operator product of cos omega x V phi, this is the operator with which you are perturbing, with itself should not generate any other operator of dimension 1 or nearly equal to 1, because if it does generate an operator of dimension nearly equal to 1, then you have to worry about the beta function of that operator. In particular, there are dangerous operators of dimension 1, which is sin omega x times v phi. This clearly has dimension close to 1, because cos omega x times v phi has dimension close to 1. Also, for example, del x, these are generic operators which could appear. However, these operators do not appear in the operator product expansion because of the x goes to minus x symmetry. The second point I want to emphasize is that the lambda dependence of omega that one finds in this computation has an analogy in classical mechanics, and it simply reflects the fact that if we have a particle moving in a potential well, then the period of oscillation in general depends on the amplitude, and this is precisely what we are saying here. Okay, now given this construction of boundary conformal field theory, one would like to extract some physical quantities from this boundary conformal field theory. So the question now is, what kind of physical quantities, classical quantities, one can extract from these boundary conformal field theories. And the particular quantity that we will focus on is the energy momentum tensor associated with this particular open string background, and this in turn is obtained by analyzing the boundary state of this boundary conformal field theory. So you could extract from this boundary state either the energy momentum tensor, but also the other conserved currents that might exist, which are associated with the sources of other massless closed string fields. And given the energy momentum tensor in the boundary conformal field theory in the Euclidean formulation, we can now make an inverse weak rotation by replacing x by minus I x0 and get the time evolution of the energy momentum tensor associated with the rolling tachyon solution. Now let me describe in some more explicit terms how exactly we go about computing the energy momentum tensor. Okay. So let us denote by B the boundary state associated with the boundary conformal field theory. This is a closed string state of ghost number 3, okay, which you can associate with every D-brane configuration, and what this does is that it encodes information about what kind of closed string source the particular open string configuration produces. Now let us consider for definiteness a D-brane system that is embedded in flat space-time in bosonic string theory. Okay. In this case, a general form of the contribution to the boundary state of course contains infinite linear combination, but the part of the boundary state that is relevant for extracting the energy momentum tensor involves only level 1 oscillators acting on the ghost vacuum. So here I have written down the relevant terms in the boundary state that we need to look at. So the Bns, Cns are the usual ghost oscillators, and these are the matter oscillators. Okay. This is of course a closed string state, and these functions a tilde mu nu and b tilde k, these are functions which depend on what particular D-brane system you have. Okay. Different D-brane systems embedded in the same space-time background will produce different functions a tilde and b tilde, and it's these functions which encode information about the energy momentum tensor. In particular, if we define by a mu nu and b the Fourier transforms of these functions a tilde and b tilde, then the natural definition of the energy momentum tensor is given by taking the sum of a mu nu plus eta mu nu times b. There is an overall multiplicative factor which can be determined from appropriate normalization, and the fact that the energy momentum tensor defined this way is conserved follows automatically by the fact that the boundary state that we have is invariant under the BRST charge. Okay. So this automatically implies the conservation law of the energy momentum tensor, and this is the energy momentum tensor which couples to graviton in coming from the closed string. Now recall that we have been considering boundary conformal field theory, which are obtained by a perturbation of this form. This perturbation is periodic along x direction with period omega, or 2 pi over omega, and so clearly the energy momentum tensor associated with this boundary conformal field theory will have a similar periodicity. So in general T mu nu will have a Fourier expansion of this form, so it can be a function of the particular spatial coordinate x which will weak rotate and the other 25 spatial coordinates that the bosonic string theory has, and we can Fourier expand in the variable x by simply by using the periodicity in x, and this is a general form. And now once we make the replacement of x by minus I x naught, all that happens is first of all that the cos gets replaced by cosine hyperbolic, and you can pick up some extra minus signs and i's coming from the transformations of these 0, 0 or 0 I components. Okay. So, if we can compute these coefficients T and mu nu from the Euclidean boundary conformal field theory, then we extract the time evolution of the energy momentum tensor in the actual time dependent solution by these formulae over here. So, the aim then is to compute these coefficients from looking at the Euclidean boundary conformal field theory. Okay. So, this is what gives the energy momentum tensor associated with the rolling tachyon solution, and I should just add that this construction can be easily generalized to an unstable de Bruijn system in superstring theory. Okay. Although I have not given the details. However, the exact computation of Tn, you can of course compute it perturbatively in lambda, but if you want exact results for Tn, then we need the Euclidean boundary conformal field theory to be solvable. And in general, not all conformal field theories are solvable, but fortunately there does exist some solvable cases of boundary conformal field theories which give interesting rolling tachyon solutions, and those are the ones we are going to describe here. Okay. And typically the theory is solvable if this perturbation happens to be exactly marginal. Okay. So, what we will do now is to code the results that one gets by applying this procedure in several cases, and I should add that the results that I will quote are valid to all orders in alpha prime and also in the perturbation parameter lambda, but strictly in the GS goes to 0 limit, which is classical open string theory. So, the first example will be that of homogeneous tachyon configuration on a dp brane in bosonic string theory. Now, a dp brane in bosonic string theory is known to have a tachyon, and the mass square of the tachyon is -1 in the alpha prime equal to 1 unit. The tachyon potential has this familiar shape, okay, which has a local minimum at on one side, but it is unbounded from below on the other side. And this particular local minimum, which I will denote by T naught, has the property that the value of the potential, the negative value of the potential, exactly cancels the tension of the BPSD of the dp brane of bosonic string theory. Okay. So, the total energy density at the minimum is identically equal to 0. So, in this situation, if we displace the tachyon field a little from its maximum and start rolling, then to linearize the order, the solution has the form as T equal to lambda cos hyperbolic x naught. Okay. And this is a situation where the total energy of the system is less than the energy of the dp brane, because the potential energy contribution, as you can see, is negative. Since the field starts at rest, the kinetic energy is 0. Okay. So, you have a negative potential energy, and that adds to the tension of the brane. So, the total energy is less than Tp. Now, here is the formula that one gets for the time evolution of the energy momentum tensor by applying the procedure that I outlined. Okay. And we can see, first of all, that the energy density remains constant. Okay. For homogeneous field configuration, this is simply a consequence of conservation of the energy momentum tensor. Okay. And we can also see that the parameter lambda indeed labels the total energy density of the system as one might have expected, and we can also see from here that for real lambda, T naught naught is always less than Tp, okay, again as we expected by looking at this picture over here. Okay. The I0 component vanishes by symmetry, and Tij is given by this formula over here, okay, where this function f of x naught is the non-trivial function which is computed by looking at this expansion. Okay. And I should add here is that to begin with, what one has is an expansion in powers of lambda times cos hyperbolic n times x naught. Okay, and one has to resum the series to get to this form over here. Now, if we examine this formula, we can say that if lambda is positive, then this function f of x naught goes to 0 as x naught goes to infinity, and that means that the pressure of the system vanishes as x naught goes to infinity. On the other hand, if lambda is negative, then this has a negative sign, okay, and then we say that this quantity blows up, this quantity goes to 0 at a finite value of x naught, namely at x naught equal to log of 1 over mod sine lambda pi, And this in turn shows that the energy momentum tensor in fact blows up. Okay. The energy density remains constant, but the other components blow up at a finite time. Okay. And this situation, lambda less than 0, we can see from this figure, corresponds to pushing the tachyon on the wrong side. Okay. Negative lambda corresponds to begin the rolling here, and it's not surprising that the system does hit a singularity as it starts rolling down. What is perhaps not so apparent is that the singularity appears at a finite time rather than as time goes to infinity. Now, a special case of that is lambda equal to half. If you set lambda equal to half in that formula, it's clear that t naught vanishes because it's 1 minus 1. But a little bit of analysis also shows that this function f of x naught that we have also vanishes identically. So, lambda equal to half corresponds to the situation where the energy momentum tensor is identically 0, and the natural interpretation of that is simply that lambda equal to half corresponds to placing the tachyon at the minimum of the potential. Because if you place the tachyon at the minimum of the potential, then of course you expect the energy momentum tensor to be identically 0. We also see from the formula over there that lambda equal to half plus kappa is equivalent to lambda equal to half minus kappa. Okay. And so this in turn shows that we cannot really place the tachyon beyond its vacuum value. Okay. That if we try to place the tachyon beyond its vacuum value, beyond lambda equal to half, it effectively corresponds to placing it before the vacuum value. Okay. And this is consistent with the boundary string field theory result that the vacuum is really at infinite value of the tachyon. Second example that I will consider is that of spatially homogeneous rolling tachyon, but not on a bosonic d brane, but on a non-BPS dp brane in superstring theory. Okay. Or this result also holds for the brane anti-brane system in superstring theory. In this case, the tachyon has mass square equal to minus half, again in the alpha prime equal to 1 unit. The tachyon potential has this shape over here, okay, and the drop in the potential at the minimum is again adjusted. Okay, in fact, it's adjusted so that the total energy density is 0 at the bottom. Okay. So, in particular, EP, this drop is equal to tension of the non-BPS d brane if you are dealing with a non-BPS d brane system, or twice the tension of a brane anti-brane system if you are dealing with a brane anti-brane system. So, the energy density here is exactly 0. Here is the corresponding formula for the evolution of the energy momentum tensor, okay, and you will recognize that this formula looks very similar to the case of bosonic string theory, except that this function f of x naught has a slightly different form. Okay. There are of course these factors of root 2 which simply reflects the fact that a tachyon in this case has mass square equal to minus half rather than 1, but more importantly you can see that instead of getting sine lambda pi, which was the case in the bosonic string theory, here you get factors of sine square lambda pi, and this means that for either sine of lambda this function in fact goes to 0 asymptotically as x naught approaches infinity. Okay. So, the system evolves to a pressureless gas irrespective of which way we push the system, and this again is consistent with this picture because it should not matter whether you begin here or here. The third example will be the rolling of a spatially homogeneous tachyon on a dp brane with electric field along the x1 direction. Okay. We will consider the bosonic string theory for definiteness, but we can generalize the results also to non-BPS dp branes. Okay. The result that one gets is that when pushed in the right direction, T mu nu simply evolves to the T mu nu induced by fundamental strings plus a gas of 0 pressure and non-zero energy density. Okay. And the interpretation of this is production of fundamental strings from the decay of d branes with electric field. Okay. I will put up the formula here, but I will not dwell much on them. Okay. Here is the evolution of the energy momentum tensor, and I have organized the terms in such a way that the square brackets, terms within square brackets reflect the energy momentum tensor due to fundamental string, and term in the curly brackets reflect the energy momentum tensor due to the rolling tachyon solution. Okay. And we can see that we can also explicitly calculate the source of the B mu nu field, and it is non-zero because you have a fundamental string charge. The fourth example is inhomogeneous rolling of tachyon. Okay. So in this case, we consider a bosonic dp brane with one direction compact effort on a circle of radius √2, and the tachyon that we will focus on is the first momentum mode of the tachyon. So this is described by a vortex operator which is cos y over √2 if y denotes the direction, the compact direction. Okay. This will describe a tachyonic mode of mass square equal to -half, okay, as opposed to -1 in the case of bosonic string theory because of this additional contribution from this factor. So if we want to consider rolling of this tachyon away from its maximum, then the solution of the linearized equation of motion will take this form. This factor of 2 is just a matter of convenience. Okay. And if we rewrite in terms of the original tachyon, we see that at the linearized level, we are considering a tachyon configuration of this type, which clearly is inhomogeneous because it has a y dependence. The answer for the energy momentum tensor is given here. We can see now that the energy momentum tensor now depends both on x and y. Okay, everything is real. Okay, f is the same function as before, okay, and this energy momentum tensor is conserved automatically as a consequence of this formula over here. Okay, I think instead of going through the details, let me just show the contour plot of how the energy density evolves in this case. Okay. So here I have the y coordinate, okay, which is in this direction. This is the spatial direction. This is the time coordinate. We see that we start with a distribution of energy density which evolves. The energy density becomes stronger and stronger near the core, and suddenly something happens here, okay, as if there is net loss of energy density at the point y equal to 0 at a critical value of x naught. So the energy density is conserved all along except at this point where it suddenly loses an amount of energy at the core, and after that it is conserved again. And the natural interpretation of this is a creation of a lower dimensional brane. We don't expect, of course, the energy density to be non-conserved, but it's simply that once you have a delta function source here, we don't really see it in the evolution formula that we have. So this can be thought of as the creation of a lower dimensional brane from the inhomogeneous decay of the tachyon. Okay, I think my time is up, so what I'll do perhaps is to just flash these two transparencies which shows the generalization of this to multiple tachyons. Okay. So instead of considering one tachyon, we could try to construct simultaneous rolling of multiple tachyons where you have n tachyon fields, so 2n initial conditions. The perturbation in this case has this form. Okay. Here these are tachyon vortex operators, these are the perturbations. So you have the 2n parameters which are the amplitudes and the phases, and these coefficients omega I of course have to be adjusted to make the beta function equal to 0. Okay. Again, we need to make sure that we don't generate these dangerous operators in the operator expansion, and this in turn requires that the coefficients omega I are incommensurate. Okay. If the omega I's happen to be commensurate, then we start generating new dimension 1 operators, and hence this analysis breaks down. So I'll just summarize. So what we have seen here is that the weak rotation of Euclidean boundary conformal field theories can be used to generate classical solutions in open string field theory which describe rolling of a tachyon away from the maximum. If the Euclidean boundary conformal field theory is solvable, then one can explicitly compute time evolution of the energy momentum tensor and other conserved currents. In case it's not solvable, we have a perturbative method for generating the solution, but no explicit analysis has been done in this case, okay, but presumably this needs to be explored. So I'll stop here.
Okay, questions, Gary?
Gary Horowitz, Santa Barbara. Are you telling us that when a D-brane and anti-brane annihilate, the energy density stays localized on that, world surface in some tachyon condensate and doesn't just get converted to closed strings, which would propagate out?
Okay, as I said, this analysis is being done at the G string goes to 0 limit.
So you turn off the coupling to the closed strings.
So in the G string goes to 0 limit, you don't have any coupling to closed strings.
But
so the idea is that this is what happens at a time scale of the order of string scale. Okay. And eventually this will presumably get deposited into the closed strings.
How rigorous is the method of calculating the stress tensor as a function of x naught that you described? Do you regard it as a rough approximation, or do you think it's a really rigorous formula?
No, okay, I think it's a rigorous calculation in the sense that you have to make a definition of what we mean by off-shell graviton to describe the stress tensor. Okay. And there can be other definitions of the stress tensor which are related to this by addition of other conserved charges, okay, which integrate to 0, because the zero momentum graviton of course couples to the total energy. Okay. So that ambiguity is there in this case, that you can add other conserved charges and call that the stress tensor. But from the boundary state formulation, this seems to be the natural definition of what the energy momentum tensor is.
Since string theory looks like very much like a theory with a lot of derivatives in the, well, in principle in the action, you would imagine there are a lot of other kinds of solutions that you could excite. So, well, in what sense could you see those from this approach, or how are you avoiding seeing those in this approach?
Okay, first of all, even though string theory has infinite number of derivatives, and naively one might think that it has infinite parameter family of solutions. Okay. I think that naive expectation perhaps is not correct, because if it really had infinite parameter family of solutions, it would correspond to infinite dimensional phase space. Right? Every field in the string theory will have infinite dimensional phase space, and you don't expect the counting of degrees of freedom, okay, to be affected by these higher derivative corrections. Okay. So in some sense one would expect that the phase space is really the n dimensional if you have n physical fields. Okay. And this is the way to construct a set of solutions consistent with that expectation. Okay. And I don't see any easy way to construct solutions which have other parameters in it, okay, that where the dimension of the parameter space is larger than 2n.
Any more questions?
Is there an interpretation in terms of non-commutative field theory of your solutions? If you added a B field or something like that, a large B field? You know that tachyon condensation can be in. The question is whether you can interpret these solutions in terms of non-commutative field theory the way analogous to the way tachyon condensation can be thought of in terms of non-commutative solitons.
Yeah, so if you add, say, to B field to begin with, okay, and try to see how the system evolves, that evolution can be related to what I showed just by the Seiberg-Witten formula. Okay, you can translate the, so in other words, given these formulae, you can work out what will happen in the presence of strong B field. But if we didn't know this, I am not sure that we can actually derive what happens in the presence of strong B field, because the presence of strong B field doesn't really tell you what happens to the vacuum. Right? It tells you how to construct lower dimensional solitons, but not necessarily how to construct the lower dimensional vacuum. And here what we are trying to describe is the rolling of the tachyon down to the vacuum.
I think we are running out of time, so let's thank our speaker.